So greetings to everyone. I'm Edoardo Iani, and I'm a postdoc at the Kaptein Institute of Groningen in the Netherlands. For today's talk, I will present some recent results of an ongoing project that sees the collaboration of many researchers from worldwide institutions, and that focuses on lens clumpy galaxies at a redshift above 3. But why are we interested in clumpy galaxies? We know that a significant percentage of galaxies at cosmic noon display an irregular morphology that is dominated by bright light concentrations, the so-called clumps. Now, there's a lot of ongoing debate about these clumps, these structures, and in particular about their nature. Indeed, the community is split among those who believe that clumps are just the consequence of very strong inhomogeneities in the dust distribution within galaxy disks, as it has been observed, for example, in dusty objects in the local universe, and those who believe that these clumps are real physical structures that are giant star-forming regions with masses up to 10 to the 8, 10 to the 9 solar masses, and sizes up to kiloparsec scales. Now, if this last scenario can be validated by observations, then hydrodynamical and cosmological simulations tell us that if these clumps are long-living structures, and with this I mean that they can survive to a star formation feedback for more than usually 100 million years, then they're likely to migrate inwards within the galaxy disk because of dynamical friction and torques, and coalesce at the very center of galaxies, where they contribute to the formation and growth of a galaxy bulge. Now, this possibility, this scenario here is strongly dependent on the star formation feedback recipes that are typically adopted within simulations, and also depend on several parameters that are typical of these clumps, such as their stellar mass. So with our project, we want to try to give an answer and possibly some constraints on both these questions. So for this reason, we have targeted a triply imaged lens clumpy galaxy at a redshift about 3.4. It has been withdrawn from a wider sample of lens clumpy galaxies by Livermore and collaborators 2015. And we have focused our attention on these galaxies because we have in our hand a very wide say data set that actually allows us to cover the galaxy rest frame UV, optical, and far infrared emission. For the UV, we have Muse wide-field mode plus AO observations and HST imaging, unfortunately, one single passbands. For the optical, we have archive Symphony K-band data, and finally, for the far infrared, we have ALMA observations. We have recently acquired ALMA observations in band 8. Now, the analysis of the ALMA dataset is still ongoing. It's been carried on by Anita Zanella, but yet I will show you some preliminary results in the following slide. Now, I just would like to mention that results coming from the analysis of the rest frame, UV, and optical datasets have been recently presented in a paper that has been submitted to the monthly notices of the Royal Astronomical Society. So hopefully in due time, the paper will be available to the community on the archives. So if you're interested in this topic, please stay tuned. Now, the first thing we have done was to investigate the morphology, the galaxy morphology, and we have done so by a two-dimensional surface brightness modeling of its properties. So here we have found from this modeling that the UV continuum emission of the galaxy can be well represented by 4 PSF-like lumps that accounts roughly for 60% of the galaxy total UV emission, plus a diffuse component. Now, the HST PSFs give us an upper limit on their intrinsic size that is of about 280 parsecs. This is a value corrected for magnification. And if we take into account recent findings by Cava and collaborators 2018, then we can associate to this size of clumps also a stellar mass that is of about 2 times 10 to the 8 solar masses. And here I would like just to focus your attention on these two estimates. Indeed, if we compare our results to the population of clumps that has been studied so far, and typically in galaxies at lower redshifts, what we're probing here is actually the low mass end of the mass clumps distribution, as well as the low mass, the small end, the size for the clumps. So this is something to bear in mind to correctly interpret our results and the results I will show you in the following slides. So this. Here you can see the data we have at our disposal from the integral field spectroscopy. So in particular in the plot, in the top left panel, I'm showing you how the UV continuum is observed with MUSE compared to the HST observations. So clearly we are very far from resolving the single clumps. The information is blended together. And for this reason, we had to extract our spectrum, kind of an integrated spectrum for the galaxy. And here I'm showing you the rest frame UV and optical spectra we have. For the UV, we can clearly see the presence of a stellar UV continuum and several emission and absorption lines from the ISM. We go from Lyman alpha down to the carbon-3 doublet, while in the optical, we only detect in the optical spectrum, we only detect the H beta and the oxygen-3 doublet emission. Thanks to all these observables, we were able to constrain numerous parameters for our galaxy. However, because of time, I will just focus on those that helps us give an answer to the questions I presented in the first slides. So one thing we have done was to be sure that what we are looking at here is a star-forming galaxy. And we have done this by checking the width of the emission lines, as well as checking the UV spectrum, looking for the presence of, for example, of the nitrogen-5 or carbon-4 in emission that we didn't detect. And actually, we also employed the empirical diagnostic diagrams that were already presented yesterday in a very nice talk by Mario Llerena, that were taken from Nakajima and collaborators 2018, and are based on UV line ratios and equivalent width. So from all these observables, we can safe exclude the hypothesis that our galaxy is hosting an AGN, and that actually what we are looking at here is just star formation. Now, to answer the first question that concerns the clump's nature, what we want to do is to understand the dust content of our galaxy. So what we did here was to leverage on both the ultraviolet and far infrared data sets. From the ultraviolet, the only thing we can do is to look at the slope of the UV stellar continuum. So we fitted it with a power law and found a beta parameter of about minus 2.5. This is a pretty low value. It means that we are dealing with a spectrum that is pretty steep towards the blue. So, and in particular, this is suggesting us that we are probably possibly dealing with a rather young and obscured stellar population. And this appears to be also confirmed by the analysis of our ALMA data. Here on the right-hand side panel, I'm showing you the HST image, and on top of which I'm plotting contours at 1 and 2 sigma, so pretty low for the ALMA detection for the continuum. So you can clearly see that we're not dealing with a very dusty objects, and so we can assume that indeed the structures we are observing in these galaxies are not just the consequence of UV light leaking through a patchy dust distribution, but probably real physical structures, these giant star-forming regions. So now we want to investigate. The other thing is the clump's lifetime, and a proxy for this is just to look at the gas removal timescale. So what we want to see actually, it's how fast star formation, the feedback is able to expel the gas, so the fuel for the clump's star formation from the clumps itself. So this time scale can be expressed as the ratio between the gas mass that is locked within the clumps and the gas mass outflow rate. Now, the gas mass, we estimated it from the Schmidt-Kennigat relation, in particular, assuming that clumps are forming stars in a star bursting mode. This is been recently observed in other works for other clumps at lower redshifts, as well as it is kind of supported by the fact that the gas mass that we obtain from the Schmidt-Kennicat relation for in the starbursting mode is is comparable within the error bars with the estimate that we can derive from the conversion of the C plus luminosity into gas mass. The other parameter is the m dot parameter here, the gas mass outflow rate that we derived from an equation by Pettini and collaborators 2000. So here you can see that the m dot parameter depends on different terms. So we have a term that depends on the outflow geometry. So we took into account 3 different possible geometrical solutions: spherical, biconical, and a double spherical sector. It depends on the neutral hydrogen column density as well as expansion velocities. Both parameters were recovered from the radiative transfer modeling of the Lyman alpha emission by means of the TLAC code by Max Grunke and collaborators, 2014. And actually, the expansion velocity was also confirmed by the analysis of the blue wings in the ISM absorption lines we detected in the UV spectrum. Finally, we have another parameter that is this X parameter. It's the neutral hydrogen fraction within the outflowing material. We do not have any direct constraint on this X parameter. So what we did was to construct some tracks that shows us how the gas removal timescale varies as a function of X. Here I'm just showing you, thank you, the different curves color-coded for the different geometrical solutions. And here I would like just to highlight how indeed, in general, most of the tracks are compatible with what could be a timescale shorter than 100 million years. So this is suggesting us that the gas removal timescale will happen in a rather short time, and that then our clumps will not have enough gas probably to contribute to play a significant role in the formation of a galaxy bulge. So, and this kind of well relates with the fact that our clumps, the clumps we detected, are low mass clumps. So in general, this is kind of foreseen by simulations too. The gravitational potential, well, of these clumps is not deep enough to retain much of the outflowing material that expands into the galaxy disk. So here I just would like to show you some take-home messages. So what we have done so far was to study a galaxy at a redshift about 3.4, clumpy, that hosts clearly 4 clumps. These clumps appears to have sizes up to 280 parsecs and masses up to 10 times 10 to the 8 solar masses. These clumps, looking at the dust content of the galaxy, seems to be a real physical structure within the galaxy and not just the consequence of dust inhomogeneities. And that appears from our analysis of the gas removal timescale, they're just transient structures. Of course, we need to constrain even better the physical properties of these clumps, higher resolution data sets, and hopefully JWST, near spec on JWST, and possibly harmony at ELT in the forthcoming years will have to revolutionize this. So we're looking forward for this. Of course, if we want to interpret these kind of structures, we need multi-wavelength data sets. Now, the future steps for these works is to, we're already in contact actually with people at the Max Planck Institute in Munich to try to simulate with ad hoc hydrodynamical simulations our galaxy, our target galaxy, to see under which conditions we are able to form clumps, and if they're indeed short or living structures, and to see according to which kind of stellar feedback recipes. And we want, of course, to investigate what is the impact that they have on the hosts, because probably they could not contribute to the formation of a galaxy bulge, but still have other important impacts. Finally, we are now expanding our analysis to a second galaxy for which we have a very similar data set, but the analysis is too preliminary to present today. And also we are defining a much wider sample of other clumpy galaxies, always at redshift above 3. And with this, I would like to, I will conclude. I'll thank you for your attention.